Okay, continuing on BSM, lecture number 3. It would be, terrible if I did 4 lectures of BSM and I never mentioned the word supersymmetry. Okay, I mentioned it. No, I'm actually going to talk about it for a little bit. Not too long though, just a little bit, because I want to connect up a couple of the things that are sort of, these are what I'm going to say is well known, it's known in the community. However, I have to say that it just serves as a sort of a counterpoint to look at the differences between what we've been talking about with pseudo-Nambo Goldstone boson Higgses and how we need to deal with technical unnaturalness problems, and then how supersymmetry comes in to resolve that. Okay. So a great reference that I like a lot is by Martin. This is Steve Martin. This is a great reference, I should say, for supersymmetry as a particle physicist would want to use it. There are many other references, many other books that are very good that go into all sorts of other aspects. SUSY is a huge subject. My TASI in '97 was titled Supersymmetry, Supergravity, and something. I don't remember. Something else that was super. But the point was the entire 4-week program was ostensibly on supersymmetry and supergravity. Okay, and so now we're going to get like 20, 30 minutes of okay. So what I'm saying is, this is if before I've been dipping my toe into this is at best like little micro droplet in the vast sea of what's there. Okay, but I am going to connect. I just want to connect up a couple of the things that we've been doing before with the Higgs and connect it up to supersymmetry. So it's a huge subject. Okay. And I'm by no means covering it in any level of completeness. I'm not even going to tell you any of the formalism. That's not that. If I started doing that, boom, all the lectures would go. Not going to do that. So I'm just going to state some things. So supersymmetry generally promotes fields to superfields. Where the superfields contain, so for example, the Higgs gets promoted to some chiral superfield, often given sort of the same name, but of course now there's a fermionic component as well as a scalar. Supersymmetry being the symmetry that relates the fermion and boson degrees of freedom together. So, so for the hierarchy problem, the key reason this is useful at all is that. Okay, is the fact that it's chiral. The superfields are chiral. More specifically, what we do with these, with the Higgs and all of the other fields, in the sense that what the chirality means is that we have effectively promoted the chirality of fermions to have scalars as well, to scalars themselves. So these all have to satisfy the chiral property that you started with as just having what would have otherwise just been in a fermion. So that's the key thing. That's what leads to all of the greatness from the perspective of a particle physics model that attempts to solve the hierarchy problem. That's the key piece to it. And so as a consequence then, so the hierarchy problem is basically solved by this chirality. And if you like, I can just say that then do I want to say, yeah, so then supersymmetric quantities, I mean sort of parameters, masses, couplings, so forth, those that are supersymmetric are technically natural. And since we've been going on and on about what technical naturalness means and why we care, I can just state that and, okay, we're good. So, I mean, you've seen all of these sort of diagrams before, but if I do the naive divergence associated with the top and a Higgs, this is, well, this with a, if you like, with the doublet on the external side was precisely what ultimately led to electroweak symmetry breaking in the pseudo-enamel Goldstone boson story, because this did have this divergence, but now with supersymmetry, the chirality says that it has to have another term that looks like this, where what supersymmetry does is to tell me that the lambda, well, okay, let's write it as this. The Yukawa coupling, let's call it Y top, sorry. Y top. The Yukawa coupling that is sitting between the Higgs and the top has to match exactly with the Yukawa coupling here. And they match because you have to treat these things the same. So once those couplings match, then there's a minus sign for going from fermions to bosons, and then it's just a matter of making sure I keep track of all the degrees of freedom. So of course, the top quark as a Dirac particle contains left and right-handed guys, so in the supersymmetric version of this, there has to be both a stop left and a stop right. Complex scalars, so that we have 4 degrees of freedom there, 4 here, and then the whole thing goes. I did this at one loop, but of course this would work at any order because it's preserved due to the chirality. So you can all just sort of put it back to there. Okay, so these couplings equal by Z. Maybe just a quick aside now. Obviously, supersymmetry does not need to be the only type of theory that equates couplings one to another. And so there was a large effort for a period of time, especially in sort of the early to mid 2000s, where people were exploring, and I should say, and they've continued to explore for a long time, other versions of where you have a divergence from the top that just exists in the standard model, and you're trying to cancel that off against different kinds of partners on this side. So this one relates the fermions to a boson, but there are other stories in which there's a fermion here and there's a fermion on that side. And that might at first seem sort of contradictory because of this business of just getting the sign here. But there are other ways in which you can relate a symmetry of one set of top partners to a different set of top partners and to get a cancellation. And these theories generally go under the name of neutral naturalness. These are theories in which, well, they're not always neutral. Some of them are neutral, some are not. So because at the end of the day, if I really am trying to get this cancellation to one loop order, all I need to do is to make sure that I have this coupling matching and that I match up the degrees of freedom. I don't actually need to make sure that these things are, say, colored under SU3. And I would say that these models obtained a much greater degree of popularity once the LHC was not finding colored top partners as it goes. Okay, so that's an entire other program. You could give whole lectures on just that. Anyone who's interested afterward, I'm happy to give you some references that can tell you about that. But okay, I just thought I'd mention that here now. All right, continue on. Yes?
Is there a definition of what is a supersymmetric quantity?
Yeah, I'll give you. I will give you some examples. I'll give you some examples. I'm not going to try to be exhaustive or definitive in things that I do. Yeah. Okay. So I said we're going to take. So it takes scalars to chiral superfields. That's what I just said here. So the Higgs, I just said, went into this. But from a phenomenological perspective, this is already a problem because the Higgs is one particular representation of SU2 cross U1, namely SU2 doublet, U1 hypercharge. So, okay. I don't know, it's just sort of a change of notation, but I shouldn't have done that. I should have just written H here. It's fine. So the scalar doublet that we've been talking about before is what I mean by the scalar here. So these are the same thing. And this is the fermion that has the same quantum numbers that the scalar has. But of course, these quantum numbers is a single doublet with hypercharge. But if I add a single doublet with hypercharge to the standard model, then the standard model is anomalous. So you get triangle anomalies. So there you have to fix that somehow. And so the usual story for anomaly cancellation is that you add, or you rename this HU, and you add a chiral superfield that is an HD that has fermion and scalar with the opposite quantum numbers. So if this is a 2, so if this is a 2 plus 1/2 under SU2 cross U1, then this is a 2 minus 1/2. And so it's a vector-like, from the fermion perspective, it's a vector-like partner, and it just cancels the anomaly directly. Okay. This is otherwise, if I had just these fields here, we would have called this a 2HDM, 2 Higgs doublet model, right? An extension to the standard model in which you have multiple doublets. Again, vast literature on 2 Higgs doublet models. Reviews, papers, large numbers of searches at LHC are going on for the scalar partners that would exist in a 2 Higgs doublet model. That's a huge enterprise, even in its own right, whether connected to supersymmetry or not. But in at least a minimal implementation of supersymmetry, you have to at least add this multiplet, and once you do that, okay, now you can go from there. This is not the only way necessarily to do it, but is usually considered the minimal way. And so when people talk about minimal supersymmetry, they usually mean you take all of the fields, you make them into supersymmetric multiplets, and you add an extra doublet to solve the anomaly cancellation. There's one other. Oh, sorry.
This concerns the anomaly in the hypercharge with the
And SU2, because it's a single doublet, right? And SU2. So the Witten anomaly as well as mixed anomalies in the standard model. Okay. There's one other small point to this. If I had a general 2 Higgs doublet model, I would have this, I have that, and I could freely use the scalar or its complex conjugate, or its Hermitian conjugate, whatever, complex conjugate, fine, it's a scalar, anywhere I like in the potential, and in particular in the Yukawa couplings. In supersymmetry, however, the rules of the game are such that you can only use this one for up-type quarks, and if you had Dirac neutrinos, then neutrinos, and this one for down-type quarks and leptons. And that goes to the structure of how you construct a supersymmetric theory. Yeah, I'll just leave it there. Again, I really am not trying to go into many details, and some of these things are seeming mysterious, and I'm making statements seem like they're just coming right out of the air, but it's, yeah, okay, fine. So one thing that happens as a result of the ability of having all of these particles is that now I can write a vector-like mass. Which is mu psi HU psi HD plus Hermitian conjugate. So again, these are 2-component Weyl fermions, so this is what the mass term would look like, right? If you want it, you can, yeah. 2 components, always the best way to work, especially when you're in supersymmetry. Okay, so I can write a mass term, but of course by supersymmetry, it can't be that there's just a mass for these. There has to also be sorry. Let's just write this. And there's a 1/2 somewhere. Okay. right? And then these masses are guaranteed to be the same by supersymmetry. This is an example, so now, to your question. This is an example of a supersymmetric parameter, right? A supersymmetric parameter, something that is a parameter for this theory. And so if it is supersymmetric, it should satisfy technical naturalness. So you can just compute the RGE for it. And I don't think I even have to tell you what the answer is. Right? It's multiplicatively renormalized, which means that in the limit that I send the parameter to 0, all right, it goes away. It stays 0.
And what symmetry do you recover? So you said when you set these parameters to 0, you recover a symmetry, no?
So supersymmetry is sort of special in this way, in the sense that there are only, in effect, it is not renormalized, or it's only renormalized by wave function renormalization, which is sort of multiplicative. And that arises due to sort of the fundamental nature of how you construct theories of supersymmetry. The deeper issues are related to properties of the chiral superfields known as holomorphy. And so when you construct, for example, a mu term, you construct a superpotential that contains this, that is holomorphic, and it's effectively that's really giving you the full juice for this, if you like. Yeah. Okay, so fine. So it sort of, we get properties we might expect to get, but of course we don't have scalars of the same mass. So right, you can see one of the properties of an exactly supersymmetric theory would be, in this case, there is a Higgs doublet whose mass is exactly the same as some set of Higgs fermions. So if we extend that to something we all know and love, like electrons, right now, we should have electrons and selectrons, scalar partners to electrons, whose mass is exactly the same, which we certainly don't have, right? So that is telling you immediately that, of course, this picture is incomplete in that supersymmetry cannot be exact. But just because it's not, but symmetries that are not exact, we talk about them all the time. We have chiral symmetries, some of which are preserved, some of which are broken, depending on different effects. We have the pseudo-Nambu-Goldstone boson story, where again we had approximate global symmetries that were protecting us there. So now, in this context, this is also, to realize a theory that will satisfy the properties that we're looking for, it has to be broken. And that, again, is an entire whole subject and entire literature on how you do that and how it goes. I will just say that you do it. So you end up with a Lagrangian total, which is something that is supersymmetric plus something that involves SUSY breaking. It's actually, it's a little bit akin to what happens with flavor physics in the standard model, in that the things that are flavor symmetric are very simple, and you can sort of write them in here, and then the things that violate flavor are sort of, involved, and there's lots of terms and so forth. And so what you end up having is, for example, in the standard model, most of the parameters are in flavor violating interactions, and most of the rest is sort of a simple set. And in supersymmetry, it's that way as well, in that there's a series of supersymmetric parameters here, and then there's a vast set of SUSY breaking parameters that can potentially enter. So obviously, one of them that has to be there is the ability to shift the scalars relative to the fermions. We know this just empirically from the electron. So the electron is sitting here. We have no selectron states that could certainly be lighter than it. And if they're heavier, they had better be much, much heavier because we haven't observed them. There are many bounds. The completely robust bound would be to go to LEP. And LEP set a bound basically at its kinematic threshold. So it ran an E plus E minus machine up to about root S of 200 GeV. So that means that the selectron mass has to be at least heavier than 100 GeV, pair production of these. Okay? So that's the minimum possible mass that you could have for that. In fact, it's probably even a little bit heavier than that, but that's the robust bound. So I have, right, so the picture is, I have the electron sitting here, and up here I have to have, right, separated by 100 GeV. And that's true of all of the particles that we know of the standard model, with the only possible exception of the top quark. Right? In the top quark, it's possible that at least one stop could be a little bit lighter, maybe. Although again, LHC searches have done extensive investigations of that, and virtually all of that space is also ruled out. Okay. All right. So, great. So we have to do something. Clearly, then what you have to do is to have the ability to give masses to these scalars. And that at first would seem like, haha, you're just if I give masses to the scalars, then I've just violated sort of the basic principles that I'm sort of starting with here. And I think it's sort of one of these interesting properties that, no, you can actually go in here and add in, for example, I just want to make sure that I'm connected up with what I'm doing here. You can go and add in a MHU squared, say this. Sorry, let me connect this precisely to my stupid notation that I'm struggling with today. There we go. So the scalar component to the up-type Higgs and the scalar component of the down-type Higgs, I can actually give them masses. And at first you would think, this looks terrible. What, isn't this going to destroy everything? No, it's not actually going to destroy everything. These parameters can be added into the theory. There's, again, a straightforward way of doing this. And all they end up doing is leading to logarithmic divergences in the masses. Okay, so these parameters now are not technically natural, but there's only log divergences. Because of the fact that supersymmetry, the way it's done over here, the way in which you break it, still preserves these coupling relationships. And if the coupling relationships are still there, then you only get log divergences. Okay. So, so let me just state that fact. So there's just log divergences of mass of SUSY breaking mass squared. Did I already say? Yeah, that's fine. Fine. When you take the MSSM and you construct something that is supposed to break electroweak symmetry, there are minimization conditions in the potential, just like there are minimization conditions in the standard model, such that you get a VEV, right? And so you do these minimization conditions here, and you find the following result. So I just said a whole bunch of steps, right? The steps are, okay, I add in these supersymmetry breaking mass parameters, mass squared parameters. That raises all of the scalars up. It will also raise the Higgs scalars up. And then I go and look for a minimum that breaks electroweak symmetry. I find it, I minimize the condition, and then there's something about the Higgs sector that needs to match numerically, if you like, in such a way that we get the correct amount of electroweak symmetry breaking. Namely, V is V246, right? Getting the right V. In supersymmetry, the condition very simply, I've simplified it dramatically, and I'm only writing tree level and dropping certain higher order terms. None of this is of any concern to us, really. Boils down to the sum of two terms. So you get a VEV that you would like to get, happens to be normalized by this combination of the gauge coupling, so SU2 and U1. Don't worry about that. And it's equal to minus MHU squared minus mod of mu squared. What is mu? Mu is the supersymmetric mass that I was permitted to add into the theory because I had two Higgs doublets. I had two Higgs doublets because I needed to do anomaly cancellation. Mu was a possible supersymmetric parameter because, right, it's vector-like. Vector-like because we had to cancel anomalies. So it's all, these are all interconnected. So that parameter enters here with a negative sign. And MH up squared also enters here, negative sign. And at first you'd be like, wait a second, negative, negative, this looks positive, if something's wrong. No, there's nothing wrong. In fact, what you're thinking should be is, I see, this sign and this sign means that if this quantity is positive, which it certainly is, and if this quantity were also positive, it actually does not lead to breaking electroweak symmetry. So basically you can't satisfy this condition, right? That's what it really means. And that's also of no surprise because I add a supersymmetric mass here, and that's giving me a positive contribution to the scalar masses. So, right, there's no surprise to how this is working. But of course, this quantity does not have to be positive any more than the Higgs doublet mass squared in the standard model potential has to be positive, and we know it's not, it's negative. So the conclusion you make here is MH up squared is less than 0. Just like the doublet mass squared of the standard model. And at this point you can be like, yeah, so what? This looks just like the standard model. Why are you telling me this? Right. There's only log divergences of these masses. Because there's only log divergences, it makes sense to consider renormalization group evolution of those parameters. That's what you do when you have logs. When you have logs, you get large logs, so you have to run to be able to go from whatever your SUSY breaking effective theory is all the way down to the weak scale. So you can look at what happens to the evolution of this parameter. And let me plot it this way. Don't worry, I'm not going to write anything down below the unitarity bound here. So here's 0. This is just a scalar mass squared. And I would say very generically what happens is, did I write this? Oh, I wrote it. I even wrote it. Okay, I'll write it. That's fine. Let's write it. Let's write the RGE, the relevant part of it. Here we go. No, maybe I don't write it. Nah, let's not write it. Change my mind. I'll just draw it. Very generically, what happens is, if down here is the weak scale, so there's, let me not label it, but let's call this, 100-ish GeV. Then this parameter is negative. It's down here, say, right at the unit yellow line. Better not call it unitarity bound. And then if I run it, I find that it does this, sort of like that. And most of all of the other scalars tend to do, I don't know, something like this. Okay, I'm drawing them as all coming together, and that is not really what I was attempting to convey. So let me do this one more time, maybe like that, maybe like this, maybe like this, like that. These are then, for example, this might be one of the stop masses. This might be, for example, one of the selectron masses. Okay, something of this type. Mass squareds, I should say, mass squareds. The Higgs, however, this one, so this is the up-type Higgs, depending on your perspective, from a high scale, you do this renormalization group evolution. It's only log divergent. It makes sense to do that. You do this, and you find it runs negative. Why? Because, now I will write the RGE. Is plus contains yt squared that. Which is to say that in diagrams we have we have stops running in loops that renormalize the up-type Higgs with a strength that is y top. And this is a generic sort of statement about what happens with Yukawa couplings and how this with Yukawa couplings between these particles, and that you get a plus sign there. So it's actually generic for this thing to go negative. There's no other, so all of the other quarks and leptons have comparatively negligible Yukawa couplings, so they don't contribute to this story in any significant way, which is also why MH down squared doesn't actually typically go negative, because there's no large Yukawa coupling in the down sector. It's not always the case. There are other caveats to all of this story, but this is the rough picture. But here the key is, once again, this famous fact that we outlined about what's the structure of the standard model Higgs or the Higgs story, the fact that the Yukawa coupling was order 1, not much smaller than 1, and not 4 pi, has come back to tell us something fundamental. If this picture were right, it would tell us something fundamental about why electroweak symmetry was broken. So the supersymmetric, the MSSM explanation, the minimal supersymmetric explanation is, you have a bunch of scalars, SUSY is broken in some way, you get a whole bunch of these parameters, you do this renormalization group evolution, it's logical to do such a thing because there's only log divergences as demanded by supersymmetry, and then you see one of these scalars gets driven negative. So this is what is known as radiative electroweak symmetry breaking. In a way, it was sort of the goal of Coleman-Weinberg a long time ago, and that sort of goal is realized here. So in the standard model, the sign is negative for no particular reason, other than we know it has to be based on observations. In this picture, you can at least have some dynamical explanation of that from this perspective of the evolution of the soft breaking parameters. You might have said, well, why can't I do this in some other theory, right? Why can't I do this in a 2 Higgs doublet model? Why can't I do this or even the PNGB models? But again, those models, we've already said many times now, there is these would-be quadratic divergences, and generally, just like the charged pion to neutral pion mass difference, the physics gets drawn up to that scale. Here it doesn't happen because of the supersymmetry. So that's why it makes sense to talk about this, and why this is one of the interesting consequences that can follow. Does that make sense?
But in SUSY, you can't spontaneously break symmetry.
Oh yeah, so yeah. Oh, there are skeletons in all of this closet. Yeah, as they say, right? You can't spontaneously break it within the sector directly. You have to break it someplace over here and then somehow communicate it from there over to the MSSM. That's right. And that is its own enterprise and takes a long time to sort of go through and see how it works. Again, there are much more. This is now, I think, up to about 200 pages or so. These are Martin's Tassi lectures from years ago, and you might think, oh, this is 1997, this is ancient, 22 years ago. But he actually keeps it up to date. and he's added sections and kept it up to date. So it's the latest version was just from a few years ago. I don't want to say that he's necessarily kept up to date with every last LHC non-observation, but he is certainly kept up to date with the rest. And yeah, so it's a good review, and it will tell you all about how you think about SUSY breaking and how it has to be communicated to the MSSM. Okay. So there's one more thing I want to say about this, which is about the Higgs mass. So one of the properties of supersymmetry is that the potential, the scalar potential, is determined. Okay, there's a bunch of scalars now, right? We have not just the Higgs, but all of the superpartners are scalars as well. But the scalar potential of all of the fields, so all of the scalars, is determined based on just the structure of the theory. So it's determined based on the supersymmetric parameters that are in the theory, and that's it. So this structure is the supersymmetric parameters plus whatever the soft breaking pieces are. So this in particular will look like so the sum over fields of, let me just write it, fields I, dagger, so these are related. These you can determine. So I'll just state what they are. I don't know how to do for each. What is it? This, I think, one for each superfield. And then this is also auxiliary, and one for each gauge sector. So these auxiliary fields come along with this extension of the supersymmetry where you have not just a scalar and a fermion, but then to match the degrees of freedom off shell, you have to have an auxiliary field. Okay, and that's just to realize supersymmetry as an off shell story. But because it's precisely that, it's an auxiliary field, there's no equation, there's no kinetic term, you can integrate it out in favor of just the fields that you already have. So from this you can take and then derive exactly the potential just by knowing what is the field content and the supersymmetric, so the supersymmetric parameters that enter, such as mu, the Yukawa couplings, which also enter there, and the SUSY breaking story. And this just gives you the whole thing. Why do I say all of this? Because I'm not even defining how I go about computing this. Well, the reason I say that is because from this perspective, you can also then get what is the Higgs potential out of this story. And now by Higgs, I have to be a little bit careful. If I had just one doublet, it would be very clear what I meant by this Higgs. In the case of supersymmetry, there's two Higgs doublets. And so there's two components that mix together, there's two components that mix together, which the lightest one I can identify as the 125 GeV Higgs. So when I do that and I write out the mass, or I should say the potential for this, so I get well, yeah. So let me write it out as yeah. So if I did it in terms of h, it would be and then I have okay. So let's do this: h squared plus whatever some numerical factor h to the fourth. The quartet coupling Of course, this is all determined, and in so in the standard model, so mh squared is, again, some number that I'm not remembering, v squared, but it's all determined by the quartet coupling. Right, so this is standard model. The quartet coupling in the standard model was something we measured based on measuring the Higgs mass, right, 0.13. But it was otherwise an undetermined parameter. It was a free parameter of the theory. In supersymmetry, there is no freedom to add quartet couplings. There's no freedom to just add that into the theory. It has to appear based on one or more of these combinations of taking auxiliary fields and integrating them out. So the potential appears basically based on the field content that you have. And in particular for the Higgs, it turns out that the quartet coupling is determined in this theory as, so what's a factor? I'm just hesitating based on a two, no, I think that's right. Never mind. That's fine. There we go. Okay. So the quartet coupling is determined based on the gauge couplings of the theory, which is to say that the quartic potential of the Higgs actually appears from the gauge terms of this theory. It appears actually right in here. So it's determined by g squared, g plus g prime squared, and then there's another factor that basically has to do with the ratio of the expectation values of the two doublets. This corresponds to mh squared equaling mz squared cos 2 beta. So at tree level, you would have expected the Higgs mass to saturate to the Z mass. At large tan beta, this tends to go to approximately 1. Okay, so that's a case of where you would realize that. So this was realized a long time ago, but of course, this is not the only contribution because of the fact that I've also broken supersymmetry. And because of that, I do get some finite corrections from the fact that the stops are separated from the top. And you can compute that too. And again, that was done a long time ago. And let me just show you what this looks like. So you go and do these calculations and add in, so you get mh squared is, oops, z squared, let's do beta, plus, and it is 3yt fourth in y squared okay. So this is coming from sort of a primordial quartet coupling at tree level and a radiative correction that is amounting to doing a top loop and adding or subtracting from it the contribution from stop loops. Top, stop. You add these contributions up to the quartic interaction, oops, along with this, and this is the dominant contribution to the Higgs mass. So, once Lepp had ruled out a Higgs below, or that the Higgs mass had to be above the Z mass, supersymmetry people, enthusiasts, were not particularly concerned because they knew there had to be SUSY breaking here, and they knew exactly the size that it had to be. Notice also that this is a finite correction, right? It's finite in that it's a log of m stops divided by m top. That's it. So in the limit that the stops come down to the top mass, it vanishes, as it must, because then it has to go back to the supersymmetric case. How big is this? Okay, so you can compute what the size is, and maybe the most relevant thing is what value of m stop do I need such that I can get 125 here. Sorry, I apologize. There we go. Yes, dimensions, dimensions, dimensions. Sorry, it's in my notes, but I didn't write it. And it's actually, all right, now let's get all the factors straight. The 2 actually makes a difference, but anyway. So you go and compute this thing, and you compute what stop you need to make this go, and you find it is roughly 5 TeV. Okay. To get MH of 125. Okay, 5 is not 50, it's not 510 to the 10, but it's also not 500 GeV where the LHC could have easily found these superpartners. So, what do you make of this number for these theories? And that, I think, has been the hand-wringing that has been going on ever since this thing was discovered. Admittedly, there was both the discovery of the Higgs and its mass as simultaneous with the non-observation of superpartners, which has, of course, led to, fewer people working on supersymmetry generally, although searches continue, as they should, because we don't know where it is yet. We know where it's not. But what made supersymmetry interesting from the perspective of electroweak symmetry breaking was that you could understand how electroweak symmetry was broken, at least from this running effect, which was ultimately related to the top Yukawa being of order 1. So you utilize this top Yukawa to get this result. And the fact that the Higgs mass itself was essentially determined because its quartet coupling was determined, and that was determined based on the structure of the theory. When you do that, and then you add in these corrections, and you found that the Higgs had to be a little bit heavier than MZ, but not that much heavier. So 125 is awfully close to where you might have expected it to be, but maybe just a little too heavy, at least in the sense that, right, the stops need to be here. Of course, we haven't probed stops to 5 TeV, we probed them to about 1 TeV. So it could be that the hierarchy problem is solved by some supersymmetric theory that has stops sitting at 5 TeV and all of the other superpartners are sitting somewhere maybe between 1 to 10 TeV. It could be. We might know after a period of time of running, we might get some glimpses in on it, or we might not. But it's at least not an inconsistent story to say this. Of course, having said that, it also means then that if I look at the parameters that I need to put in here to match this value, I need to take, so now if everything is sitting at, TeV scale or above, then this thing is also TeV scale or above. This is TeV scale or above. And it has to be such that MH up squared is just a little bit more negative than this is, right, than this is. Such that you get this, right, this whole thing to be a little bit positive, right? But then that means I have to cancel a TeV or multi-TeV squared number with another TeV or multi-squared TeV number. And so I end up with tuning, right? Fine tuning. And the tuning, as you can just tell from here, is at least 1%, I would say, okay? Maybe worse, maybe fractions of a percent if you're really thinking about scales here. But again, this is for the stops, whereas here I'm talking about sort of Higgses. So
isn't the LHC working at 13 TeV?
Oh, yes, they are. However, remember, it's a proton-proton machine, which means that the to be able to produce, so first of all, you have to produce stops in pairs. That's already going to make it difficult. And then you have to suffer Parton distribution functions, right, of the quarks. Right, so the highest energy events at the LHC are dijet production, and I think it's on the order of 7 or 8 TeV. Right, the bounds on colored particle production are typically at the TeV-ish scale. Some can be up to maybe 2 or 2 and a bit TeV, but that's the territory. Right, it's on that order. Is what the bounds are. Of course, it depends in details, right? I mean, I'm saying this very quickly. I mean, obviously, it depends on how does it decay, depends on what is the various production modes and so forth. The details matter. I'm just trying to give the broad, just, if I didn't say anything on supersymmetry, it would have felt very weird to me. So I wanted to just say a couple of things about why it has a connection to the Higgs sector and what that connection is, and you know, why there is some degree of tension that we have to suffer with. Okay. So we see supersymmetry needs 1% or more tuning in such a way to match the electroweak symmetry breaking. We see pseudo-normal Goldstone boson Higgs has constraints from the S parameter and from the non-observation of rows and the non-observation of their top partners. That leads also to a tuning. Maybe not as bad as here. It's hard to judge these things. Maybe 10%. Okay, maybe 5, you know, something of that territory. Okay. All of these ideas that are trying to address the hierarchy problem seem to be in tension, right, with the non-observation of new things. Not in tension so much that you just completely give up, but enough so that it makes you wonder about working on something else. Okay.
What about the masses of the other scalars? There's a selectron.
Right, good. So there are, again, the LHC does extensive searches for all of the super partners, basically, and the bounds on the supersymmetric charged leptons, so selectron, muon, tau, they depend sensitively on how they decay. Well, not so much, sorry. They depend sensitively on how they were produced, I should say. So you can obviously produce them by Drell-Yan, you know, you just do photon and pair production. If you do Drell-Yan production, the bounds are very weak because Drell-Yan itself is a small production rate. If, however, you produce them through other means, then you can create larger rates. And as long as the decay has enough visible energy you can see, then there are bounds of a few hundred GeV. So it varies between sort of a LEP bound of 100 to up to maybe a few hundred GeV.
And from a theory perspective, for example, on your picture, you drew the selectron as being more massive than the stop.
You mean here?
Yeah.
That was completely arbitrary, and I'm really all I wanted to indicate was there's by no means any. I did not want to indicate these were all coming together at a point. So you could shift this down, you could shift this up, you can move these around. Yeah. If you're asking why did I even draw them the way that I did, it has a little bit to, well, and maybe even this electron I shouldn't have drawn that way. I probably should have drawn it like this. Anyway, if I'd been really thinking carefully, I should have drawn it like that, but fine, okay. Again, this depends in detail on who's talking to whom and the RGE contributions. So typically what happens is the super partners to the gauginos will tend to drive up particles. They'll drive up their masses because their contributions to the RGE have a negative sign, okay? And interactions with Yukawa couplings tend to drive things down. And of course, that was of course the famous result of YT squared. So I'm well aware that I have said only a few things. I have hardly defined even some of the terms that I'm using here, but I'm just trying to give this little bit of this little flavor of why this picture has been in our minds for a long time and where, you know, I think roughly speaking where it sits now.
Can you explain why the Higgs potential is set by the gauge coupling?
So it comes from calculating the scalar potential from these auxiliary fields. And so there what you have to do is you write out you write out your full theory, your Lagrangian, in terms of the supersymmetric fields. So the fields, their superpartners, and the auxiliary fields. The auxiliary fields have no kinetic term. You integrate them out, which means you solve for what Fi is and you solve for what D are in terms of the other fields of the theory. In this case, D is the auxiliary field of a gauge supermultiplet. When I solve for that, that links it to any chiral superfields who talk to that gauge field. So in the case of the Higgs talks to SU2 and talks to U1. So when I integrate out that auxiliary field, I get quantities that are the Higgs scalar field squared for D, and then I get D quantity squared. And that gives me a scalar to the fourth. And the reason they came with a G squared or G prime squared is because it came from one of those gauge supermultiplets. So I've just said it in words without deriving it. It's derived here. I just wanted to give you the words. You asked, so it's good. Yeah. Okay. Any other comment? Yeah.
What are the constraints on beta?
Fine. Yes, there are constraints. Okay. Roughly speaking, it's not much lower than tan beta, can't be much lower than 1, and can't be much larger than about 60. And the reason for those two numbers you can understand from when tan beta is order 1, you have roughly equal VEVs, which means each doublet is roughly contributing to electroweak symmetry breaking the same amount. If you take the standard model Higgs doublet VEV and you split it into 2 VEVs, then I've lowered the VEV by a √2 factor, which means I have to increase the Yukawa by a √2 to compensate, right? So all the Yukawas have to be cranked to compensate, if you like, for that. And so as I take tan beta small, I tend to push the top Yukawa more and more above 1, and eventually I get to that non-perturbative point. If I go in the other direction, if I take tan beta very large, that's taking V. I should have written. You don't even know what 2 and 1 means here. This is D and U. Sorry. This takes the down type Higgs very large relative to. Oh no, it's the other way. Did I do it right? No, it's the other way around. Sorry, it is the other way around, and then I can explain that too. Here we go. It's the other way around. So if I take tan beta large, this is then taking VD very small. If I take the down type VEV very small, it means I have to really crank on these Yukawas, right, to the down type Yukawas to match the fermion masses that we observe. And so eventually I get a non-perturbative B Yukawa. So those are the limits, roughly. Other questions?
So if one wants to explain the G-2 tension
Yep.
with supersymmetry,
Yep.
As far as I recall, it requires large tan beta.
Yes, and there you can also understand that because if you draw that diagram, okay, so mu on G-2, here we go. So the standard model electroweak looks like this. There's a photon somewhere. Yeah, somewhere, right? Here or there. And right, this contribution is on the order of, what is it? The current discrepancy is on the order of 2-ish times the electroweak contribution. That's my memory, right? Something like that. Yeah, it's of that size, which is suggestive because if that anomaly persists and we think it's real and it's not light by light scattering and it's not hadronic vacuum polarization uncertainties or whatever, if we believe it's real, then it would suggest there needs to be a contribution that is of the same order as the electroweak contribution. And that, of course, was suggestive long time ago when this anomaly was first sort of realized in the Brookhaven experiments in the early 2000s. Because now, of course, I can do diagrams like this. Okay, and again, a photon is going off the end somewhere, and I have a muon coming in. I have a smuon here, smuon there, and a muon there. This is usually done here. Okay, so now I have a gaugino that runs in this loop and muon, and so you can see that I basically need I need these super partners to be all of the order of sort of the mass of the W to make this go. However, there's a caveat to that, which is that if this is so the contribution which arises when this is simply a supersymmetric partner of the gauge field has then only gauge strengths here, and since we know that the masses of these have to be larger than the masses of those, it basically means this diagram is a little bit smaller than that one when I incorporate just the gauge effects. So one alternative would be to make this a Higgsino, which would at first seem to be a crazy thing to do because the muon doesn't have a large Yukawa coupling, but this could be a down-type Higgsino, and if I go to large tan beta, the VEV goes down, the Yukawa goes up, all of the down-type Yukawas go up, and so as a consequence I get an enhancement, a tan beta enhancement. So that's the origin of that, and that's why this type of diagram with down-type Higgsinos is contributing in a way that could be larger even than the electroweak contribution, roughly. Other questions? Now's your chance, because I'm switching topics in just right away. So I'll warn you right now. Some of you are thinking, thank God. Yeah, go ahead. Please.
About the direction of the arrows for the muons, so it looks like you put a Majorana math.
No, I really was doing this. So this was a case where I started drawing two different diagrams. In one case, I drew one. If this had been a gauge coupling, if this was a gauge coupling, then I would have put the left-right chirality flip as an external muon. It could have been here or here. It doesn't really matter. If it's a Higgsino, it's different because now there is a chirality flip that I can do here because it's a Majorana particle.
And for the first diagram on the left?
Here. So here, this is the muon mass. And again, I'm just denoting it as if it were a mass insertion. But remember, right? So muon G minus 2 is precisely that which connects mu left with mu right through a F mu nu interaction, right? The usual magnetic moment.
Usually, the propagator will put only one arrow. There are two arrows in the same direction, right?
Right. Sorry. So this is in the sense that this is sort of that's what I mean. Okay, so it's in a chirality basis rather than in a mass basis. Yeah, so I'm sorry, I can understand your confusion now. I previously was drawing arrows when I had Majorana masses sitting in there, and yeah, this is not a Majorana mass, it's just a mass to flip the left to right chirality, that's it. Yeah. Whereas over here, I can do this chirality flip with a Majorana mass, with a real Majorana mass of a gaugino, with a gaugino. Let's leave it at that. Okay. Where's ready? Here we go. Everything's getting erased. The BSM physics that I'm most excited about is dark matter. So, at least basically for the rest of the lectures, we'll talk about dark matter in some form or another. So I did contact Laura, who had given you wonderful lectures on cosmology and early universe physics, and she told me she sort of touched on freeze out of probably neutrinos, maybe freeze, but didn't really go into dark matter much at all. That was what she told me. If you tell me differently, then suddenly I'll have to go and review her lectures and find out. But I'm going to assume that, and then we'll move on. Again, at summer schools, you could easily give multiple different sets of different lectures on dark matter. For example, last year's TASI had, I think, 3 or 4 different people giving lectures on some form of dark matter. One person talking about dark matter theory, one talking about like direct detection, and one person talking about axions. Okay, so you can give multiple lectures that just go on and on about this, which I don't have. So I have to, again, pick and choose and do a few things. So that means I'll be a little bit more elementary, but I will give you lots of references to different things that if you're interested in, you can go to. I think, you know, if I were to give a colloquium on dark matter, of course I would run through all of the evidence very clearly, because sometimes there's always the odd person who still has this sort of strange notion that they think that dark matter is not there, or I don't know. I can't understand it these days, but let me just at least list off the evidence in words. So these are the big ones. This is the historical one, galactic rotation curves. This one has also been there for a while, and is people who do n-body simulations have known for a long time you need dark matter to make the universe look like the way we see it. Weak lensing provided a great example of this in the form of the bullet cluster, which is perhaps the most famous one, although I believe there are others now, in which you can use the gravitational lensing of 2 clusters sort of going through each other to verify that the dark matter went through and the gas gets left behind, and it's a really cool thing, cool piece of evidence. I think the one that just sort of kills off all of the standard arguments about trying to do gravity in some other way or trying to modify it this way is CMB. Right, because the CMB now has measured, okay, a small little aside. So I got into the field in the mid-90s. In the mid-90s, there was a satellite called Kobe. Kobe had observed the first density perturbations in the universe. Basically the first L of 2, 3, 4, something like that. That was about it. Okay, and there was like, haha, we've seen density perturbations in the universe. This is awesome. Okay, right? It was great. I even remember distinctly. I was in undergrad, and one of the newspapers. So I went to undergrad at the University of Toronto, and there's like the Toronto Star or Globe and Mail or whatever it was had this like, you know, big color picture, right? You know, right there on the newsstand that you could see. That was the Kobe map that they had, and it's like this image sort of burned into my brain. Like, oh, this is awesome, right? Cosmology we're discovering things. Okay, I had no idea what it meant at the time, but I thought it was very cool. Yeah.
But you can have that matter which effectively behaves like moon. For instance, if you have. For instance, in the superfluid matter modulus can condense in gravitational wells and create a Mondrian phenomenon. I'm
highly skeptical of those, but that maybe is best for offline discussion. So yeah, okay, good. So the CMB at least is this amazingly powerful set of observations, which now have L's that go out to several thousand, and the, you know, you can do this fit to the cosmological parameters, which is of course the baryon abundance, which is the stuff that talks to photons, you know, the dark matter abundance, which is the stuff that doesn't talk to photons and doesn't respond in the same way, and of course the fluid all of the other components of the fluid, radiation density and so forth. And it matches it so well, when including dark matter, that it's just it's a really remarkable piece of evidence. So, at least since the mid-2000s, we've had sufficiently precise data on CMB that, this is, okay, we got new physics, we got to find it. There are other things, so-called baryon acoustic oscillations, which is again in some way related to doing large-scale structure. I didn't do that. Did I do that? Okay. Anyway. Oh, great. Thank you. Fine. All right. Clearly, I shouldn't talk about that. So, all right. There's also indirect evidence. BBN is consistent with a matter abundance that is a few percent. So if you have some piece of evidence like this that tells you about the total matter abundance, you have another piece of evidence that tells you the baryon abundance has to be only a few percent, you immediately deduce that, oh, there's got to be something else. So indirectly, this definitely provides useful data. And, of course, supernovae were how we discovered that the universe was accelerating its expansion, which is, of course, consistent with all of the observations that we have from CMB now on the total energy density of the universe. Tomorrow, I may actually make just a couple of words about this. So again, if you're here, maybe it'll be fun. Maybe I'll turn the mic off. Anyway, okay, we'll see. Let me quickly just write. I'm going to squeeze this in here, and I'm going to write slowly. I'm going to try to write slowly. Here we go. 7, 8. Ah! Here's a small list of people who have given lectures at various summer schools, including here in past years, but also at TASI and other places, that also discuss dark matter from a number of other different perspectives. I will not be able to even cover anything at the level that all of this material is doing, so I'll just take a few select topics and talk about those, okay? And that's what I'm gonna do. But I wanted to make sure I give you all these references right now. And if you're interested in any particular aspect of it, come and ask me afterward, and I'm happy to try to point you in the direction that you'll find information that's useful. Okay, what do we know? Well, what do we know about dark matter? As a fraction of the critical density of the universe, it's roughly a quarter, which may or may not be related to the fact that that's roughly 5 times the baryon abundance. It's dark. In fact, there was a paper that quantified how dark it was, and very roughly, it's, oh, what's the number? TV. Oh, That doesn't make sense. Oh, yeah. Shit. Here we go. What did I put? I think there's some uncertainty on this, but okay, let's do that. This is from a paper of 11. Oops. Oh, I give up. 10, 11, 2, 9, 7. That is to say that the electric charge has to be smaller than 10 to the minus 4 with some loose dependence on the mass. It has to, there are bounds on the self-interaction that actually come from here. Bullet cluster actually provides the best bounds on the self-interaction, which is the interaction of dark matter with itself. And that is 1 in these crazy units of, okay. Cross-section divided by mass. It's a little weird, but this is really just coming from the fact that the interaction rate scales as n sigma v, the interaction rate of dark matter. So if instead I rewrite this as the energy density, then I have a sigma over m. And so if I go to a cluster, I see a cluster with some energy density of dark matter and some characteristic velocity. So basically I get a bound on this quantity. Okay, so that's where it's coming from. So we have this, and these units are crazy. Like, who knows what that means? But it turns out nucleons, I mean, astrophysicists and their units, I don't get it. I really don't. I mean, what's wrong with, okay, anyway, it's fine. GeV, they could just, it's fine. Okay. So if you do nucleons, this quantity is about 10 in these same units. If I did my conversions right. Okay. So this is one origin of, or one place where there's bounds on the self-interaction. There's also bounds from suppressing small-scale structure. And by that, I mean small galaxies. Okay. There is a great review on this topic alone here, 1705, 02, 3, 8.
This bound is not that strong. I mean, because nucleons, they interact strongly.
Strong's relative. The bound is not that strong. That strong is relative to what? Yeah. So relative to nucleons, it's not. Yeah, it's not that strong. I agree. Okay. But dark matter is certainly not a nucleon. So at least at that level, maybe, yeah. Okay.
You are meaning interaction between
dark matter and dark matter.
But asymptotic states, no? So if there are models in which dark matter is strongly interacting, but then I guess this is the bound. So say you have hadrons of dark matter.
Yep.
This is not a bound on the things that bind the hadron, but the interaction between hadrons, no?
Correct. Exactly correct. Yeah. Okay. Comments. Okay. It's cold. Unlike Mainz a few weeks ago, right? Which means it's non-relativistic. And there's a whole bunch of evidence to this. The large-scale structure n-body physicists have known this for years, maybe decades. When they simulate large-scale structure with hot dark matter, it's very clear that it just qualitatively doesn't match what we see. You don't get the structures that we observe. You don't get hierarchical structure formation where small-scale structures form first and they build up to large ones. That doesn't happen in hot dark matter. So this is definitely it's definitely cold. And there's, as I said, there's a whole bunch of different pieces of evidence to this, including CMB as well, that has constraints. What else do we know? So lifetime. Well, you seemingly have galactic rotation curves that have dark matter, so that suggests dark matter lived until now. So it at least has to be the age of the universe. But you can actually do better than that. If you have a random dark matter particle and you just turn on a decay interaction, you take its whatever was preserving its global symmetry and force it to decay. Then you can set a bound on its lifetime, and you find that it has to be greater than approximately 10 to the what numbers did I write? And then maybe I'll justify them. But yeah, roughly 10 to the 8 to 12 times universe. Much, much longer than the age of the universe. Okay. Essentially, you can integrate over time all the way back and let dark matter particles decay and accumulate all of their decay products, and invariably they end up being too much for indirect detection if you have a decay time that's shorter than this. I don't have the reference for this, but I can give it to you. Anyone who wants, there's several references on this story. Okay, so we have the lifetime. Okay, now specializing slightly, let's imagine it's a single particle. You can ask what is the smallest mass that it could have? Well, that actually depends on whether it's a boson or a fermion. If it's a boson, (10 to the minus 22 eV. At this point, we're not really talking about it as particle dark matter. We're talking about it as some coherent scalar field, some large occupancy number of a sort of a scalar field. So it's not a particle per se, right? But this is the lower bound, and that comes about because if I compute the wavelength associated with this mass, it's 1 over m or 2 pi. There's 2 pi's h bar to h. I don't believe how many minutes I wasted on that. Anyway, 1 kiloparsec. Okay. And the point is that if you took the mass smaller, you will make this scale larger, and so you'll still suppress small scale structure. So basically the existence of dwarf galaxies, the existence of small galaxies, and that they formed and exist today, we observe them, is setting this lower bound. And again, there's some futz on this number, but it's close enough for our purposes. Right, kiloparsec. Okay. If it's a fermion, there's a different story. And there, it has to be the mass of the fermion has to be larger than about 1 keV. So now we're not so much talking about, we are really talking about particles when we think about these scales. And of course, this is just coming from Pauli exclusion. You pack a bunch of non-relativistic fermions inside some small scale structure, and you ask how many can I put in of some mass, and stack them all up, and you discover a bound. This goes all the way back. There's early papers that did this, but you can also look at Kolb and Turner, and they discuss the fermion bound. Okay. And again, this is this is a single particle. This is a single field. Is how we want to think about it. There's also no detectable interactions with matter. Well, that is aside from gravity. Right. All of this evidence that we have here is gravitational in origin. I mean, I don't mean literally we observe we observe the indirect effects of dark matter through its gravitational interactions on the CMB large-scale structure and all of these things, the power spectrum of galaxies, so forth. So, okay. So this is cosmologically, broadly speaking, some of the things that we know. This should begin to inform us a little bit about where we want to look for dark matter, or I should say how we want to construct models of dark matter, and then sort of how we look for it. Of course, I also didn't tell you an upper bound yet, so I will do that soon. Let me just look at, and I'm just thinking, okay, I'll do two more things and then I'll wrap up. So I might take about 5 minutes into the break.
Can I ask you something?
Yes, shoot.
So this last point for which you mentioned, what's the difference of that and that the dark matter is dark?
Correct. These are, in effect, that's right. So the difference here is, I had in mind when I said no detectable interactions, I mean we don't see direct detection. We don't see the direct scattering of dark matter off other particles. That's really what I mean by this, which I'll quantify much more in detail in a little bit. Whereas here, I'm just giving you an example of the notion that if you even imagined it had some milli or micro electron charge, even then there are constraints depending on the mass. That's all. Okay. All right. So what did I do this? Right. So pretty much all of this has been cosmological. You can ask about dark matter locally, and you discover that, well, it's mass density locally, so rho at r equal to r sun, the radius of the sun around the galactic center, is about 0.3 in GeV per centimeter cubed, which is to say that if dark matter were a WIMP of 100 GeV, we've got 1 per liter. One of them is in your head right now. Well, it's not staying there. It's actually moving really damn fast. So you actually have them going, all the way through. Okay. How fast? Well, that's the speed. V is of order 10 to the minus 3. Or, if you prefer astro units, a few hundred kilometers per second. So that's what I mean by fast. Okay. This is coming from simply the fact that we are actually even moving within the dark matter halo, and so as a consequence, our movement, which is related to the stability of, the disk and blah blah blah, angular momentum conservation. Similarly, a major component to that is then that the same dynamics that is setting our speed is also setting the local speed of dark matter, in effect. Now, of course, there's a distribution. No one knows what the velocity distribution of dark matter is. What we do know is that there is an upper bound on the velocity distribution at v escape, which is to say that if I plop a dark matter particle in right at r of r dot of a particular speed, okay, admittedly, if it has a particular speed and I aim it in the right direction, then it escapes the galaxy and it never comes back. That's approximately 550 kilometers per second. Plus or minus. There's at least 10% error on that, okay? What it looks like in between, we don't know. You can do simple models of it. One model of it makes it look sort of like a Maxwellian distribution. This is a common thing to be used when people do direct detection, but it's an assumption. It is backed up, however, by n-body simulations. So n-body simulations will typically get a distribution like this, except that it's not smooth. It may do this. It may have little spikes, little streams, and so forth. Okay, but you know, I mean, if this is, seems like some distribution like this is interesting. And there may be even better ways of trying to get at the distribution using observations. We'll have to see how that pans out. This escape velocity also means that that in lab frame, there's a max speed. So lab frame means us, means the Earth. And that's approximately v whatever dot plus v escape. So we're moving around the galactic center at about 220 kilometers per second. Escape velocity is 550, so this is about 770. So this would be precisely if dark matter, if as we're moving in the wind of dark matter, right? So it's some halo with completely random directions where it's going, but with this sort of rough speed distribution, and then we're moving in this halo, so it has to be a dark matter way out on the tail that happens to have been moving directly toward us. We're moving directly toward it, so that the relative velocity in lab frame is maxed out here. The fact that we're moving it means it is highly directional, right? There is a dark matter wind, and if you want, you can turn. Look over there. Look over there. You can see. You can feel the wind. You think I'm joking, but no, it's coming from sort of over. Actually, I should check. Hang on. One moment. There's a great app for this. Where is dark matter coming from? Where is dark matter coming from? Hang on. Oh, what is it doing to me here? There. Yeah, it's right on the horizon. Yeah, it's amazing. We're moving in the galaxy, right? So we're moving towards some star system, and that star system happens to be Cygnus, the Cygnus constellation. So as a consequence, from our perspective, dark matter is heading toward us from Cygnus, which right now happens to be right at the horizon in that direction. Okay. Is that relevant? That depends on whether the direction of the dark matter is relevant for either the model and or for the detection strategy. Okay. And that we would have to go into models to figure this out. Okay, the last thing I'll end with, and which will be the first thing I start with tomorrow, is I just want to put the mass range of dark matter up, because it's a big range. There is a range. Okay, it's 10 to the minus 22 eV. We got that bound from, or did I erase it? No, it's there. Never mind. It's there. That's if it's a boson. Where do I want to do this? Maybe here. 1 keV fermion. Weak scale. 100 TeV. That'll wait till tomorrow. And then, why I wrote that scale. And then, all the way up here, we can do on the order of 100 solar masses. Sorry, stellar masses, excuse me. Sorry, 100 suns. 100, did I say solar? I said solar. Sorry, for a moment I thought I said Earth, but anyway, I apologize. So yeah, 100 solar masses. So obviously the range is broad, to say the least, but there are some constraints and there are some restrictions on it. So, okay, that's fine. The character of the particles, or whatever the dark matter is completely different generally as you go in this space. When you're way down here, you're generally of one variety of dark matter. Once you start going north of about a keV, you're of a different variety. You get to around the weak scale, and typically then there is a morphing of a certain variety here into a different variety there. This variety tends to keep going to 100 TeV or so. You go up above 100 TeV, then you have to do something different again if you want to get to here. And then as you go all the way up to, what is this? What's the mass of the sun? 10 to the 57 GeV or something like that? It's 10 to the 57 protons, so I'm going to call it 10 to the 57 GeV. So this is 10 to the 59 GeV in some maybe nice units. But here we're talking about collapsed structures like primordial black holes. I would say that at this point, this area here is of dubious I just used the word. I probably shouldn't have said it as another word. It's dubious whether this can be all of dark matter. There we go. I said it properly. It could be some of dark matter. Typically, the fraction has to be less than about 0.1. So that means omega PBH less than 0.1 of omega dark matter. By dark matter, I mean the 0.25 number as we would measure today. Okay. So while there could be primordial black holes that make up some small fraction of dark matter, it doesn't seem to be the dominant set for various astrophysical constraints. So in the end, I think this is something we don't need to talk about. All right. So we're actually going to end up we're going to go down on this side of things and look at candidates down here and see what we learn from them, which I will do tomorrow. Okay, thank you.
Interaction, I was under the impression that small-scale structure problems actually say that the self-interaction has to be greater than some value, right? But then I think you mentioned that it's because of bullet cluster makes sense, but then I didn't understand the suppress the small-scale structure thing that you mentioned. So you're exactly correct that there are some people. So there are always puzzles in astrophysics, and astrophysics is famous for puzzles in which one camp will say, "You need new physics to solve this puzzle," and the other camp will say, "It's astrophysics." Small-scale structure problems, puzzles, as they say, are exactly in this camp. In that we don't know yet whether they are really require something new, or whether it is simply something due to our modeling of galactic structure, for example, baryon interactions or supernova effects and so forth, whether those are leading to the issues. Now, having said that, if you take the point of view that there are real problems with small-scale structures, that is to say that we need to suppress dark matter interactions at small scales, then you do need a self-interacting dark matter is a way to do that, and then you need to run right up to this bullet cluster bound to try to solve that. The story is even more complicated than that, because the cross-section that I gave you was assuming there was no velocity dependence, right? Because remember, the interaction rate was the dark matter mass density sigma over m times v. But I could have said sigma was a function of velocity. And if I do that, it's possible that you could imagine a cross-section that is low or lower at high velocities where the bullet cluster is, and that the cross-section rises as you go to lower velocities. This, in fact, happens exactly with QCD baryon interactions, right? Baryon scattering is a classic case of something where there's a velocity dependence that is there, and you understand exactly where the velocity dependence is coming from because it's pion exchange, right? So once you increase the velocity of the baryon-baryon interaction, then eventually it starts to turn over and get smaller as you go to higher velocities when pion exchange is important. So, yeah. Other questions?
A few weeks ago, there was a piece of news that they had observed a galaxy without dark matter, supposedly.
Yeah, I think I've heard. Yeah, I've heard this in different contexts. Perhaps it may. The question is it, so this is one of those classic things of how do you learn physics, right? Do you learn physics by taking large amounts of data, putting it all together, and then just deciding some basic principles that you get from it? We also gain large amounts of knowledge by looking for all of the exceptions to a case, right? So, we talked about flavor symmetries in the context of the standard model. If we ever see muon go to E gamma or charged lepton flavor violation, we will immediately learn a new fundamental principle of the universe because it's an exception. The problem with astrophysics is you never know whether the exception, something that doesn't have dark matter, is something I'm supposed to expect from astrophysics or whether it's something that's unique, that requires some explanation. And I honestly don't know what the story is there. My impression was it's not a problem, but I'm not an expert.
Okay, then I think we can break for coffee. Thank you.